Hello, good afternoon. Thank you. Thank you all for coming. It's absolutely a great pleasure to be here today and to introduce Josh Perozek's PhD defense. When I was coming here, I was thinking, okay, what can I say to introduce him? What are the thoughts that come to my mind? And there are three thoughts that I think I wanted to share with you. The first one is about the magnitude of the problem that Josh has been trying to tackle during his PhD. I was in Washington, D.C. this morning, attending the annual meeting of the CHIPS Act. And there they emphasize some of the things that we all know, such as, hey, data centers are taking over the world and the power consumption in these data centers is extremely high, reaching today around 4% of the US energy production. But it's difficult to know whether that's really big or really small. And so one of the speakers mentioned, for example, when you search something in Google these days, you get this paragraph at the very top generated by ChatGPT. That is actually consuming 8 watts hour of energy. 8 watts hour. So you can basically turn on a light bulb for an hour with the energy that you are using to power one single search in Google. That's partially the problem that Josh is trying to tackle with his PhD. How do we manage how do we do the power management for this data? The second thing I wanted to share about Josh is that he's amazing. I mean, of course, he's extraordinary, and he's the kind of student for whom everything. Okay, I have two hypotheses here. He's the kind of student for whom everything is easy. Every project you give him, yeah, he just does it. It works. Either that, or he's the kind of student for whom I am amazing advisor, and every single idea I share with him is successful right away. Not sure which one is true, but I'm leaning towards the fact that he's amazing. And the third thing that will always stay with me when I think of the time that Josh has spent in our group here at MIT is that he's very brave. And I didn't say that. My daughter, who at the time was probably 7 or 8 years old, we were in an outing, the entire group, including my kids. And Josh somehow went into the goods and he was walking around and so on. And Sophia, my daughter, came to me and said, "Oh, Josh, he's very brave." He was going to some creeks or something. I mean, she was impressed. And she still, when we talk about Josh at home, she still tells me, "Oh yeah, Josh, that really brave student that you have." So indeed, I mean, Josh has been amazing. It has been a tremendous pleasure and honor to work with him. He has been tackling a really difficult problem. I guess he needs to be very brave to be working on that, and he has obtained really amazing results while at the same time helping to start a company like Fabulous and doing many other things on the side. So Josh, I'm looking forward to your defense.
Great. Thank you so much for the very kind words, and thank you all for coming today. I'm very excited to share my work on expanding the design space of vertical gallium nitride power devices. So as Tomas, is this going to go? Having some technical, there we go. So as Tomas kind of pointed out, this is, power electronics it's a big space. There's a lot of problems to be solved there. Power electronics are everywhere. They're in the grid interfaces for renewable energies like solar and wind farms. They're in the motor drives for electric vehicles and electric aircraft. They're in the power converters that let you charge your laptop and let you charge your phone. And they even, as was mentioned, deliver power to really like life critical things like ChatGPT. going into kind of like the data center route, if we look at, just one of these examples, just to kind of narrow in on the problem we're trying to solve here, we can look at something like a UPS. All this does is really provides power to one of the additional steps to get power to a data server. If you go inside of that, you'll find a power circuit like this one. This is the most simplified version of a boost converter that you can draw. And if you look inside of that, you'll find a power transistor. And that's what the focus of this work is mostly on. As a semiconductor engineer, I like to think that this is the most important part of this. People who design all the rest of it might disagree, but it is where a lot of your losses come and where a lot of the inefficiencies that we're trying to tackle today arise. To really kind of simplify exactly what we're trying to do, this power transistor just behaves as a switch, and it does two things. So in the on state, it conducts current. We want to just have the lowest resistance possible. If you have low resistance, you don't have to have as many devices in parallel. It makes your circuits much simpler to make, and it makes the heat generation go way down. And then in the on state, if you turn your switch off, it needs to block very high voltages. If you have a high breakdown voltage, you don't have to stack your devices in series. It makes your circuits much simpler to work with because you don't have to deal with all the voltage offsets for each one. And if you can operate further away from the kind of breakdown voltage, you'll have more reliable devices. So with those two kind of main metrics that we're looking for in any of these switches, how do we make a good one? Well, it turns out that the theory to making these is actually relatively straightforward. There's a very simple relationship between the breakdown voltage, that VB, and the on resistance. We want that on resistance to be as low as possible. And what we have control over is this bottom portion. And this is the Baliga figure of merit. It's commonly cited anytime you talk about power transistors. And all of these, importantly, are material parameters that are constant with any material system. And that's why we like gallium nitride. For gallium nitride, that number is the biggest. Makes it pretty simple to benchmark all of these. And the way we'll always present this, and you'll see this plot a lot of the time throughout this thesis, is just looking at what is the on resistance for any given breakdown voltage for all of these materials. And you'll see we have a whole bunch of labeled lines here. And these represent what we'll call the 1D unipolar limit. And we'll go back into why that name's so long further along in this presentation. But what we want to be is in that bottom right corner of here. And that represents when you have a high voltage switch that is a very low on resistance. But the physics say that you have to be in the upper left. So our goal is, how do we inch towards that? And one way that we've been able to do that, silicon's the furthest upper left one there. That's what most of the power electronics, or really any semiconductor that you'd be familiar with, is made out of. And one of the easiest ways to improve this trade-off is just switch materials. We went to silicon carbide and now gallium nitride. That lets us have lower resistive losses for any given breakdown voltage. So in the gallium nitride space, what are we working with? Well, by far the most common device, 99% of transistors made out of gallium nitride are what's known as high electron mobility transistors, or HEMTs. These are lateral devices. They're really great for RF, high communications or high-speed communication circuits, things like radar. They are not good for power devices, which is what this work is focusing on. There's a couple of reasons for that. One is kind of the lateral design. Some people were talking about, there's a vertical qualifier in the title of my thesis. This is where that comes into play. So the lateral design means that all of your contacts are on the top surface there. You've got your source, your gate, and your drain all on the top of the wafer, and your current flows across it. If we want to make a high voltage device, we have to increase that spacing between the gate and the drain. It just takes up more area and make a longer device. If we want to increase the current, we need to make a wider device. So we only get one dimension to make a high current device. And that's true of all lateral devices. Specifically for gallium nitride, though, we have another problem, and that's that we can't dope gallium nitride in the lateral dimension. All of the carriers within here are created through a polarization difference between an algan barrier and a gallium nitride layer. That's great. It gives you very high mobility. It's bad in that you can't control how much charge is there. So we're never operating at the optimal trade-off point between dopants and distant that lets you really maximize the breakdown voltage for a device. We get around this by playing tricks like having field plates and things, but as you can see from the electric field up there, it's not uniform, it's peaky. That adds kind of problems to your reliability. And along with that, with everything being close to the surface, we're very susceptible to surface effects. So if anything kind of, if moisture absorbs onto the surface, it's going to change the behavior. It's why HEMTs have just been notoriously unreliable in power systems. in contrast to this, what we focus on here at MIT and we've really developed and pioneered is the vertical GaN FinFET, which is a vertical architecture. This is kind of a switch that silicon and silicon carbide have done for as long as they've been power devices. And the idea is that instead of making a larger device to scale the voltage, you make a thicker device. Our voltage now scales in a third dimension, which lets us keep everything very compact. And we can now scale the current just by having a larger area device. It's a 1-to-1 ratio there. Also with gallium nitride, all of these are grown epi layers. So we put it in an MOCVD reactor and we grow this, nanometer by nanometer. And during each of those, while it's growing, we're able to very, very accurately control the dopants that go within it. So, within a 10 nanometer span, we can go from 10 to the 19 silicon atoms per cubic centimeter to 10 to the 16. We can have very sharp profiles there, which lets us really optimize the electric field and kind of make sure that we're pushing up against that 1D unipolar limit that I talked about. And then there's some other benefits in that, the heat's generated uniformly, everything's compact, so it switches faster. But those are more second order effects that won't be as important for the rest of this talk. So to motivate why we care about this specific one, it's been a while. When I first arrived here in 2019, our group published this paper on, record switching figure of merit that we achieved for our 1.2 kilovolt transistors. And what this really means is that these devices should be the best possible devices that are available today to go in all of those applications that I mentioned on the first slide. So hopefully that kind of provides some background and context on why do we care about these devices? Why do we want to spend, 7 years of a whole PhD trying to improve how these work? So with that motivation, I'll talk into a little bit about how they actually work. There we go. So the structure of these devices is actually somewhat straightforward. So if you take your way from the backside, you've got your drain contact, and on the top you have a very narrow fin, think 100 to 500 nanometers wide, a micron tall, and on top of that you have your source metal. Normally you would have electrons flow from the source to the drain through that fin, but on the sidewall of the fin we've added a gate structure with the gate oxide. If we put a negative bias in that gate, we're able to fully deplete the fin, and when there's no carriers within the fin, that current doesn't flow. We're in the off state, our transistor's off. As we increase the voltage on the gate, that depletion region formed within the fin shrinks until a narrow channel starts to form in the middle. That's the onset of threshold, and our device starts to conduct some current. And if we keep driving that gate voltage more positive, there's an accumulation layer that forms along the sidewall of this fin, allows electrons to flow very freely between it, and now we're in the on state. So relatively straightforward in how they work. How we make them is a little bit harder. The first ones we ever made used this process of build up, put on photoresist to planarize the surface, etch it back very carefully with an oxygen dry etch, and then whatever's exposed after you etch back the resist, you can etch with a different etchant. And when you're done with this, you can get a very nice FinFET cross-section over here. On the right is a cross-sectional SEM that we took in a fib of these devices. And it's really great for, one-off demonstrations. But the problem is what actually happens when you spin on photoresist is it's never actually flat. You'll have surface tension and curing shrinkage and edge effects that all lead to kind of a domed shape over your fin array that you have. And when you etch that back, the profile stays there. So you're going to never have a very precise way of etching back this photoresist layer. And your device is going to have some potentially, fatal defects within it. So really, anytime we have large area devices with this process, edge effects limit the repeatability, the scalability, and the yield of these. And this brings into my work on expanding the design space of these devices. We're going to talk about kind of 3 different ways that we've tried to approach these gallium nitride devices. The first is very novel fabrication techniques for increasing yield and uniformity within these devices. Next, we'll talk about how we're able to expand this to a wafer scale process. And finally, look at what can we do next once we have the world's best FinFET? How do we keep improving? So going first into how we can improve the manufacturing of these devices. One of our first attempts, when I first came here, I just tried to replace photoresist with silicon dioxide. We can use, PCVD-based systems here to very accurately put on thick layers of oxide that kind of locally planarize the surface. And you can etch this back and make the same FinFETs, which we did. And they worked okay. But the big problem that we found is that this is the output curves of the transistor. Is it has a very shocky turn on. You can kind of see this. This should be a straight line here, but it looks more like a diode. And that kind of ruins your on resistance and is not ideal for any power applications. Really, you want that to be as straight and vertical as you possibly can. And what we found is that all of these etch back steps where you put the silicon dioxide on, etch the silicon dioxide back, is exposing the gallium nitride to a bunch of fluorine ions. Those implant themselves into the surface, they cause damage, and it degrades the contacts. We see like a 20x increase in the contact resistance, and that's being generous. It's incredibly non-ohmic, so you can't even really talk about contact resistance in this sense. So while we're able to get a repeatable, fully vertical design, what we couldn't do was avoid these damaging dry etches. It was a source last fabrication, so putting the source contact on, you had to go through all of these damaging steps. And it really still required that you be very careful with etching back these steps. I would spend literally days doing a single etch, going back and forth between an electron microscope and the dry etching tool, which was really difficult when those were in different buildings. So that took some time. So to see how we can kind of address this problem, we take a step back and we look at, well, why is this the case? And whenever you hear about, like Intel or TSMC coming out with a 3 nanometer process or something, they're always talking about lateral dimensions. And that's really the only way that we can control these precise layers in nanofabrication. Everything is 2-dimensional. We can look at the surface, at the wafer from the top, and we can draw shapes on it from the top, but that's all we can do. This is great for digital circuit applications and stuff where you want to be able to route stuff very effectively, have it all compact, but it makes 3D structures much harder to make. Also, with just kind of the way that all these process works, we're really just depositing and etching material, which means you have to work from the bottom up. Things that are lower on the wafer have to be put down first. There's some tricks we can play and have played using directional depositions and conformal depositions, and then mixing that with isotropic and anisotropic etches, but it becomes very tedious and tricky to work with. So the first thing we notice is that we have very non-planar structures, so we don't need to use the planar processing techniques that have been, dominant in the silicon industry for so long. And one of the first ones we looked at was, what if we just tilt the sample? So if you take your fin array that you have, this is a very simplified sketch of the fin array. If you tilt it and have a directional deposition, so think snow falling down on a surface, at an angle, those fins start to form shadows. And those shadows prevent any material from depositing there, and you can start to pattern things along the top of your fins instead of the bottom of your fins. So that goes against the bottom-up approach that has kind of dominated the silicon industry. And this isn't exactly a new idea. People have been tilting samples in e-beam evaporators. They use it for very advanced, surface preparations and optics studies. They've done it for some quantum computing type devices, but they stop after just kind of one deposition. And what we do is, what if we just kind of take this idea and we run with it? So, you might imagine we can flip it on the other side. We can do a second deposition. We can keep our structures more symmetric. Where it gets a little more intense is if we now use the overhangs that we just created and make more shadows with them. So if we tilt it at a less extreme angle, the region underneath what we call the mushroom of a mushroom structure also forms a shadow. And we can keep using this to build up and eventually have a sidewall structure. So that's where we have metal along the sidewall of our fin here. And now it's starting to resemble a FinFET, but our actual devices are way more complex. But, there's for those of you that have worked in nano, we do have one evaporator that lets you change an arbitrary angle or set an arbitrary angle on your evaporator. That is the slowest pumping and dirtiest evaporator that we have. So it's not ideal for these kind of really trying to push the limits of these devices. So we did have to go and build our own mount that lets us set any arbitrary angle. So I've just placed this in a 6-inch wafer holder within any evaporator that we have. You can set the angle with a digital angle finder to within plus or minus 1 degree, which ends up being more than sufficient accuracy for these, even sub-micron features that we're trying to make. And it lets us use all of the fast pumping, high quality, diverse material systems that we have in the lab. So this was kind of a key enabler to letting us really try this and iterate quickly as we go through these. So now I'll talk about how we actually fabricate, the world's first self-aligned vertical GaN FinFET. The process is a little complicated, but hopefully quite interesting. So the first one that we need to do is we have to have 4 regions patterned along the sidewall of these fins. The first one is a field oxide. This is a spacer between your gate and your drain that prevents the gate oxide from breaking prematurely. And the goal is to just have oxide at the very bottom of these trenches. So what we can do is we can form that same mushroom structure that we had before. We can use aluminum for that. And then if we come in with nickel, we can do the same sidewall structure and kind of pattern that along the base there. We can do 3 different depositions. Ideally, it would be rocking and you could have it uniform, but if you just do 3, you can sufficiently cover the bottom. And what was crucial is that if you use different metals, you can have etch selectivity to them. So we can now undercut that aluminum with even just like photoresist developer, TMAH. We'll undercut that. We can lift off the nickel on top of the fins. We're left with just nickel on the bottom. That is now a good mask for etching our silicon dioxide, which we can use an isotropic dry etch or a wet etch to remove our nickel, and then we've got our silicon dioxide at the base of these trenches. So it's a little more convoluted than just etching back a single layer, but it's the only way that we've been able to find that you can actually repeatedly put this layer at the bottom of the fins without just destroying the gallium nitride with high intensity plasmas. To keep making the FinFET, we can do a source first process. So now before we put the gate metal on, we can put the source. Same exact mushroom structure that we had before using our Ti aluminum as ohmics. We align that to an N+ region on the GaN to make nice ohmic contacts. And now since it's a source first process, we can then make the gate. So we put down our gate dielectric. We do the same thing with the nickel. We use nickel because it has a beneficial work function offset between the gallium nitride. It lets us increase the threshold voltage. But the key to this is that between the source and the gate metal, we're always going to have our gate dielectric. That means that this gate should never touch the source because it's self-aligned, but if it does, it's still okay because we have the gate dielectric. So it really improves how robust this process is. Takes it more, there's no longer an art in making these. It's just a science and you just follow the steps. It's a standard recipe. To finish it off, it's kind of the same stuff that we've always done. You planarize it with more oxide, you etch it back, open a via, but now the gallium nitride's all protected, so that's totally fine, and nickel's actually super robust, and we remove it anyways in the next step. Put our contacts in, or remove the resist, put our pad metals on, and we make these devices. As you can see from this cross-sectional SEM here, we're able to get a very close match. This was, the first attempt at making this. We achieved sub 500 nanometer gate length on these FinFETs. Entirely self-aligned, follows exactly the process that we had described. Without any restrictions on lithography, all in the first shot, which was great. It wouldn't be great if they didn't work. They do work as very good power devices. We have very sharp turn on and our on off. It's about 6 orders of magnitude limited by the measurement equipment, which is always a good place to be. And the turn on is very ohmic. It's nice and straight, nice and vertical. And then while we're talking about this technology on the fabrication, it's also been used in our lab in a couple of other very interesting projects. One was some good work by Pauchon last year, where he was able to make the first integrated anodes on gallium nitride field emitters. So we were able to use that angle deposition to close off an air gap in a vacuum transistor. And then also some work by Sharon in using a very similar structure and modifying it slightly for optically controlled transistors. So that was some of the fabrication technologies that we were able to develop to really improve the yield, the repeatability, uniformity of these devices. But we're still making them on very small pieces. And what we want to do is we want to scale to a wafer. So all the work so far has been on very small pieces of bulk gallium nitride. They're about the size of your thumbnail or a postage stamp or so. And what we want to do is bring it to an 8-inch platform. We want to make it about 200 times larger. This becomes a lot more challenging. There's a lot more uniformity that you have to take into place or take into consideration. One of the biggest problems with doing this is just where do you even buy 8-inch gallium nitride wafers? They're all, what we've always seen is gallium nitride grown on silicon. And the problem with that is when you grow gallium nitride on silicon, you're growing these things at like over 1,000 degrees Celsius. It's very hot. And if you look on this plot, looking at the coefficient of thermal expansion for these materials, you'll see that as it cools from those high temperatures down to room temperature, the gallium nitride is going to shrink a lot more than the silicon. And if you're above a certain thickness, that gallium nitride just cracks. It turns out that thickness is between like 5 and 7 microns. Past that, it's very challenging to make, but we need double that. We need about 15 microns of GaN. So we've been able to partner with this company, Chromis. They've been providing substrates for this work. They have a very nice engineered substrate that is thermally matched to gallium nitride. So you can grow arbitrary thick layers and they cool down at the same rate so that nothing cracks. In addition to this, you also need a place that can run 8-inch wafers. That is currently not MIT Nano, although that hopefully will be coming in the near future. But we've been lucky enough to be able to work with MIT Lincoln Laboratory in their microelectronics lab. This is a production class 90 nanometer CMOS facility that has full 8-inch wafer processing capabilities. Even more importantly, they've worked with gallium nitride before. They've worked with 3D circuits and really kind of novel integration schemes. And they even have their own gallium nitride growth capabilities. So they're kind of the most ideal place to be doing this kind of work. And thanks to them, we were able to demonstrate the first full wafer fabrication of these devices. I actually did bring one that we can pass around. I do ask that you don't open it, but it is quite nice if you get it in the light. It's kind of cool to see. Yeah, so this is the first demonstration of gallium nitride FinFETs on a 8-inch platform. And again, just like the last time, they do work. They're very nice transistors. They have the same kind of on-state characteristics. What is different with these, though, is that these were the first ever made. We kept it conservative, and what we didn't include was what we call the field oxide. That was that first step in the last process flow I showed you. And the importance of that is at the base of these fins, you have a sharp corner for your gate. And corners are really bad for any semiconductor device. It amplifies your electric field and tends to break whatever's there. What we can do is put in silicon dioxide. It's very strong. It can handle high electric fields, and it kind of reduces the effects of that corner. We didn't have that, so all of our devices broke at 25 volts as expected. That's the breakdown voltage of our gate oxide. It does take a little bit longer to run these through Lincoln Laboratory than it does for me to just go in the lab and try to make these. So we do have several more, I guess, one more wafer run is currently underway, hopefully done within the next couple of weeks, and then another one following that. But the next steps are really, we want to increase the thickness of the epi layers, actually make this something that can support 600 or 1200 volts. We need to incorporate that field oxide, and then eventually we have to fully remove that substrate that I said was so great for working with because it's not actually conductive. So for a vertical device, you do have to take that off. Those are underway. I hope I can report back to some of you with the results of that. But that has been our efforts on scaling these wafers to an 8-inch platform. And as we're on our way to actually having commercializable gallium nitride FinFETs, the question then becomes, well, what's next? How do we extend the performance beyond that 1D unipolar limit that we had previously discussed? So, as you recall this slide from earlier in the presentation, I had mentioned that this is all for 1D unipolar devices, and you may ask, well, how do you overcome the 1D unipolar limit? You just get rid of those qualifiers and you use 2D bipolar physics. Sounds simple in theory. It's actually kind of hard to implement in real life. But when we do that, we're able to remove this dependency on the breakdown voltage where it's a squared voltage, and we just have a linear dependence with it. And that means that as we scale the voltage, the resistance grows much slower. It ends up for gallium nitride at about 1 to 2,000 volts. We can have a 10 to 100x improvement in theory by using these types of devices beyond the unipolar limit. This has been used in silicon. On this plot, I have a whole bunch of different random data points from various devices you can buy. And you'll see a lot of silicon ones are actually past that line, and they use exactly this structure here to make that happen. There's three approaches that people have done to, or have been able to figure out to make this happen in silicon. There's the PN junction, or PN superjunction. There's a field-plated drift region, and there is a high K dielectric drift region. And I should add a disclaimer that throughout the rest of this, I'm going to be using the word superjunction to describe all of this. It describes that bottom portion down there below the intrinsic transistor. And despite using the word superjunction, they don't all have junctions. It's just kind of how the field has decided to describe a lot of this behavior. So then how do they work? For our normal 1D unipolar devices, to establish an electric field that lets us have a high breakdown voltage, you have to remove all of the electrons from the device. This is done by the drain voltage. As you ramp that up to 1,000 volts, it makes a very large depletion region that depletes your whole epi layer. And you aren't able to remove all those carriers until you're essentially at breakdown voltage. What you can do instead is you can put in a PN junction that is parallel to your conduction path. So it's not, you're not crossing this PN barrier. You're just next to it as you're conducting. And what that does is it lets that depletion region extend sideways instead of vertically. This means at a low bias, we can fully remove all of the carriers. It also, if you were to just really dive into the math behind it, it decouples the Poisson equation that governs how all of this works. Lets us have a uniform electric field, which means we can have a shorter drift region, and therefore the resistance goes down. It just scales linearly with length, so that improves the resistance. But the real win is that since we can more easily remove charge carriers, we can put in way more dopants, 10 to 100 times more dopants to still be able to deplete them. And this is the big win for superjunctions. It makes the on resistance way lower. But it's not all great. The problem is that you have to perfectly match the charge balance within those p-type columns and the n-type columns. So the blue and white regions there have to have the exact same number of dopants. If you don't, if you're just off by 30%, which when we talk about these dopants, we're talking on log scales. An order of magnitude is, if you're within that, you're pretty accurate on your doping. 30% is very easy to miss, and it can decrease your breakdown voltage by up to 50%. It very rapidly falls off. They've been able to solve that in silicon, but the problem for gallium nitride is there's just really no way to dope these. Silicon can use ion implantation or kind of fancy regrowth techniques. For GaN, that doesn't exist. There's no reliable diffusion, there's no regrowth, there's no ion implant that lets you change the carrier types within any of these regions. So that kind of just immediately rules out PN superjunctions as a problem that I can tackle without growth experience. So what we can look at instead is a field plate type drift region. For those that are familiar with HEMS or like LDMOS devices, it's the same exact physics, and it's also the same as the PN junction devices, except for we deplete the carriers laterally with a MOS capacitor instead of a PN junction. So it's the same exact thing. As we reverse bias that MOS capacitor, we remove all the carriers laterally. The physics are a little weirder. We actually need a linearly graded doping profile. So it starts low, ends high. Overall, that means we incorporate less dopants than before, but still more than the 1D unipolar case. So it's still a win. And it was used successfully in silicon before they made the PN junction type devices. The problem with here is that oxide that you have in the MOS capacitor that's extending throughout your drift region here, it needs to be very strong. The entire breakdown voltage of your device will be seen across that oxide. In silicon, that's fine because silicon dioxide is about 30 times stronger than silicon. But it's only about 3 times stronger than gallium nitride. So your whole device ends up being just dominated by the thickness of the oxide needed to put this in there. And it becomes very hard to overcome the loss of area that you get by having to put so much oxide between there. So that leaves us one other choice. That's the high K dielectric superjunction. This a little more confusing to wrap your head around, but the idea is that you have a perpendicular plate MOS capacitor, and the permittivity of this material is so high that you're able to still deplete the carriers laterally by the electric field lines extending down through that high permittivity material. going sideways and depleting the carriers. Just like before, it lets you, have a more uniform electric field, and it also lets you reduce or increase the doping density within here to reduce the ion resistance. And now the only question is, well, how strong does the dielectric has to be? Well, in this case, it only has to be as strong as our semiconductor. So that means we have a little more room to play with than just, silicon dioxide. And it needs a high permittivity, but exactly how high does it need to be? If we look at available materials, we'll see that there's plenty that are in the 25 to 100 range. Whereas for context, gallium nitride has a relative permittivity of about 10. So these are better than GaN, and the dielectric strengths are between 2.2 and 7. There is not a whole lot of literature reports out on there, so verifying that is questionable, but for gallium nitride, it's about 3 to 3.5 megavolts per centimeter in our dielectric strength. So we have at least 3 materials that are possible for this kind of structure. So we decided that this would be kind of our approach for establishing, the first superjunctions in gallium nitride for this. And my first attempt was just take the standard engineer approach and just try to simulate it. Just spend all the time with the computer, make as many as you can, see if one of them looks better. I spent hundreds of hours, did 300 plus simulations on these, and none of them were better than the 1D unipolar limit. It's very easy to make this better if you just throw out all considerations of making something you can actually fabricate. These were all done under that kind of restriction, and I wasn't able to do it. So I took a step back, decided to put, dust off the old math textbooks and go with the mathematician's approach, try to find an analytical solution to this. It exists. It's very messy. If you add more layers, it becomes many pages long. But there's a key assumption that the doping density within it is uniform, and that might not be the case for the optimal device. We saw for the field plate devices that we needed a linearly graded doping density to really maximize performance. That might be the case for these. We didn't know, so we decided to put our engineering hat back on, but try to be smarter about it and go with a numerical simulation, but implement everything ourselves. So we created some software that would kind of solve the discretized Poisson equation, which describes the physics of all of this, and lets us customize everything. We can, change all of the doping densities and permittivities of all these layers. We can add field plates, and most importantly, we can modify the doping arbitrarily to maximize the Baliga figure of merit. So that's kind of where do you fall in that plot. We want to improve that trade-off of breakdown voltage and ion resistance. Running with this, it's way faster than using commercial software because we were able to tailor it specifically to our devices, and we can do massive sweeps of the design space. We kept things, again, something that we could fabricate. So we didn't go with oxide thicknesses greater than 200 nanometers. All of these are deposited by ALD, so any of the staff back there that sees that would have a heart attack even talking about 200 nanometers. But we put that as an upper bound and started looking at these and found that we only need permittivities greater than 20 to make this improve past the 1D unipolar limit. And there's plenty of materials that let us do that. We've got hafnium dioxide, zirconium dioxide, two which are used very frequently in the semiconductor space. Then we have titanium dioxide, which is a little more experimental, but has way bigger permittivity, around 100 instead of like 35 or so. If we look at kind of what these solutions themselves look like, we talked about the doping profile not necessarily being uniform. It turns out a kind of U-shaped profile is key for these medium dielectric constant materials. As you go to something with a permittivity like 1,000, something that's never really been demonstrated, it can become flat. But as we're trying to squeeze all the performance we can out of it, we need to tailor that doping profile to be, optimal, which we're able to do there. As we do that, we also see that our electric field becomes more uniform, like we had talked about, lets us get a little more breakdown voltage out of these devices. And on that plot that we had shown before, we're able to slowly inch past that 1D unipolar limit. And again, I should stress the log nature of this plot. It doesn't look like that line moved very far, but it's a pretty substantial improvement in terms of your ion resistance. So we know what we need to make. The question is, how do we make this? These devices require very deep, high aspect ratio fins. Some key things to know around gallium nitride fabrication is we always make these, all of our etching is done with a nickel mask. Nickel has about a 20-to-1 selectivity to gallium nitride. And for these fins, though, we want aspect ratios about 50-to-1. That means that any nickel that we pattern is going to be extremely tall and extremely narrow. And if you've ever done liftoff of nickel, that's kind of just a recipe for disaster. It's nearly impossible. With our devices, we need about 300 nanometer line widths over a micron tall of nickel. Very difficult. Nobody wants to let you do that. And then the last thing unrelated to that is for all of our fin fabrication, we do have one big advantage in GaN is that we have crystallographic wet etchants. So if we use TMAH, we can actually align the fins to the right sidewall. And no matter how dirty our etch is, if we use this wet etch treatment, we can make almost atomically smooth sidewalls in our gallium nitride. So we took these ideas and we decided to combine them with the fabrication techniques that I talked about in the first section of this. So we start by just making our normal fins like we would for any transistors. We use 50 nanometers of nickel, we etch a micron fin. We want to go way deeper than that. So we're able to use those same mushroom structures that we created and remask the gallium nitride. So we remove the mask from the first one, we put on another one, etch it deeper, we clean it up with TMAH. We remove the mask again, we etch it deeper, clean it with TMAH, and then strip the mask. We do it one more time for a total of 3 times or 4 total etches. And we're able to make very deep, high aspect ratio fins here. And again, as we're done with this, we remove the nickel there, and we can do our final step of the mushroom structure to put on the actual Schottky contact, because in this case, we're making diodes with that same exact mushroom structure. This is very similar in the fabrication flow. If you're familiar with the Bosch process for DRIE etching, it's kind of a cyclical way of remasking your etch as you proceed, and you're able to make very high aspect ratio etches in silicon. The benefit for that is it all happens in one tool, and you can just walk away as it's a thing for a couple hours. This does take days to go through, reapply the mask, etch it down, and go through. So it's quite tedious, but in theory could be combined into one tool one day. But to finish off the devices, once we have those very tall fins, we just fill them with the high K dielectric, we planarize it with oxide, we put on our pad metals, and we're able to actually make the devices. And this technique, we're able to demonstrate the highest aspect ratio fins ever made in gallium nitride. They're about 70-to-1 aspect ratio in the most narrow case. And they're so narrow that the gallium nitride actually starts bending. If we were to go any further than that, you can see this image on the right. These fins are just leaning into each other. So we're kind of pushing against the limits that you can do with GaN without having some form of extra support within it. To go into the performance of these diodes, they behave as you would expect for a Schottky diode. We have, greater than 10 to the 6 on-off ratio. There's low hysteresis. That specific on resistance, about 1.4 milliohm square centimeter, which is, we'll benchmark that in a little bit. So they work as diodes. The CV curves become a little more interesting. You'd normally expect for a Schottky diode for this red curve, the 1/c² term, to be linear. Because our doping profile is nonlinear, you see that effect come up in the capacitance there. And the most interesting behavior of these is actually in our reverse breakdown characteristics. So as you deplete this, normally you'd expect for any diode that your leakage current just increases continuously. But for these devices, you actually see that it dips down in the middle. And it's very strange behavior for any sort of diode. And the reason we believe this happening is because these diodes kind of act like a diode-tied reverse biased MOSFET. So the dielectric on the sidewall there is essentially your gate metal or your gate oxide for a FinFET. And as you deplete the channel more and more, you're essentially lengthening the channel of your gate and you're removing short channel effects. So when there's not very much depleted, you can't deplete these fins laterally and you can leak through it very quickly. But as you make it, you deplete your entire drift region length there. Now your carriers have to go through 6 microns of a gated transistor, which reduces the leakage. And once you hit 600 volts, as you see in the simulation, you've depleted the entire drift region there. And that's when your leakage starts to increase again. So just an added effect on the weird physics of kind of how these devices work. With the same simulations, we can see that at 1,000 volts for the fin diode, the red curve there, the electric field is about 30% lower than you would have for just the planar diode without the fin there. We can benchmark this against other devices in literature. You'll see that we weren't able to surpass the 1D unipolar limit with this. We'll go into why in a second here. But I think what's important is this is benchmarked against the most optimized Schottky diodes in literature that have been, 10, 20 years to be made. And this is the first one ever made of this, meaning that there's a lot of room for us to still improve this and eventually surpass this, make this surpass the 1D unipolar limit in gallium nitride. But the expected breakdown voltage was 1,600 volts, not 900 volts. So why didn't we hit that? Well, we took all the devices and we used that simulation software that we had created to see, well, what should have been, what's actually breaking. And we're able to fit it by modeling the breakdown voltage of the zirconium oxide. These light circles here represent the ideal case for all of these devices. And you'll see that if we say that the oxide breaks at 2 megavolts per centimeter instead of 4, we get a very close match with our devices. There are some in the very small case where fins were bending, we had bad fabrication. And in the planar case, they're actually incredibly leaky because without those fins there, you weren't able to actually turn off the diode. We compared this with some capacitor data. So the blue curve there represents the zirconium dioxide. It was co-deposited with our devices. You can see the best devices there, these were just with MIM capacitors, had a critical electric field around 2 megavolts per centimeter. Very closely matches with what we had simulated. So really the key is to improve these devices, it becomes how do we improve the oxide? Thankfully, this is on the low end of reported oxide critical electric fields. So there should be room to improve this through some types of proper seeding or annealing treatments you can do after the fact. And then other ways these failed, I talked about bending. That was by far the most common way that these failed. If your fins bend, you don't conduct through most of the fin, you don't get the high K dielectric between there, and they break early. And the other thing is that there was no edge termination used for these devices, which is very strange, but the fin diode has intrinsic mesa isolation in that the edges are always etched all the way down through the drift region. So it does ease a lot of the edge termination that you would typically need for these type of diodes. And what we can do looking forward, well, there's, as the growth technology catches up, there might be ways that we can either use regrowth or ALD to incorporate some type of P-type oxide. People have been successfully using nickel oxide as the P-type material instead of gallium nitride. We can look at ferroelectric or other high K materials that in pulse conditions offer these same high permittivities. MinSiC is doing some really great work on ion implantation of gallium nitride. We can start to see how we could, implant in between these narrow fins, try to change the polarity that way. And then eventually we need to incorporate these into transistors. That'll be the next step. And we've been able to develop process flows. I have an image here of one of how we can incorporate the self-aligned FinFETs that we created and the high K dielectric diodes and combine them into one ultimate device. So hopefully with that work, you've seen how we've been able to increase the yield of FinFETs, scale them up to wafers, and start to explore, well, what's next? And with all of this, I really need to, thank my thesis committee, Professor Palacios, Bergen, and Peralt. Appreciate all the support and patience as I've been, rushing to get this done at the end here. And it's just been really great getting to know you guys and share my work with you. I also have a whole list of people that have been making this possible. A lot of this work is sponsored by an ARPA-E program where we've been working with Lincoln Lab, UCSB, Chromis, and Analog Devices. There's too many people to obviously go through all the names, but you've all been invaluable in making this happen. Also, the MIT Nano staff and everyone who has been with me since, when we were working in 39 together. I've learned so much from all of you guys. It's been truly a pleasure spending the days in there. It's very refreshing to be able to have a normal conversation with you guys when we're just waiting for tools to go, and I appreciate all of that. Also, applied materials has been very helpful. It turned out it's not easy to have a PhD based on experimentation when the whole world shuts down, and then at the same time we're transitioning clean rooms from 39 to nano. There were a lot of times when tools were down or we didn't have something available. And Applied Materials, and the people over there were able to help us, run a lot of our pieces as we ship them out to them. And then everybody who's been in the clean rooms with me, it's been really wonderful. Learned a whole lot there. And finally, I need to thank the ND-SEG Fellowship who supported a lot of the first years that I was working here. In addition to that, the Palacios lab, I've spent so much time with all of you guys. It's been really great. From the very beginnings, all the senior students who taught me everything I know, to watching all of the younger students, progress through their journey. And most importantly, I need to thank Greta, who's not able to be here, but is responsible for setting all of this up and really just in general keeping the lab going, along with Joe, who was our admin when I first arrived, and taught me everything. I think when you get a new puppy, you have to dedicate a whole slide to them. This is Juniper and Claire. They have been endlessly supportive. Really, hard day in the lab. This is what you want to come home to. They're really great. And then obviously all of my friends and family I've made along the way. My family is endlessly supportive, especially you kind of have to be when you say, I want to go to college for 7 more years. They're there right there for you. And all of my friends who have made those 7 years just really enjoyable. It's some of the best part of my life. And if you're not pictured here, it is your fault. You should have taken more pictures. And then finally, the Blocks boys and the GAN girls. You guys have found good ways to distract me throughout my PhD. And I'm really looking forward to see how we can shape the semiconductor world. With that, I want to thank you all. Hopefully you learned something. I think it was enjoyable, and I appreciate you being here.
Thank you. Thank you, Josh, for a great talk. We have a few minutes for questions. Who wants? Don't be shy, please. Okay.
So you mentioned that the final the diodes, right? They're roughly 6 microns deep. How deep do you think ideally they should be? I mean, I know they are leaning on to each other, but if there were some way to strengthen those, how deep should they go?
Yeah, so they're actually about 8 microns deep because you have to go a little bit further there. Ideally, you could use all of that 8 microns for the supporting the voltage. We don't currently. That'll buy you another 500 volts in your breakdown voltage. But the depth of that is entirely what determines what the operating voltage of these devices are. So if you wanted to go to a 10 kilovolt device, it's going to need to be way deeper, but then you're going to run into those structural problems that we had discussed there. There's also some concerns. There is a there's sidewall depletion that occurs, and eventually as you go too narrow with these devices, they're just intrinsically pinched off, and it makes the resistance go back up again. I think we're kind of pushing up on the limits of exactly where you can fall within that space. I think you could maybe go 10 or 12 microns. I think fabricating them would be hard, but not impossible. But I think that's kind of as far as you could really go.
Thank you. More questions?
So to ask about the 8-watt light bulb example, from the beginning, if you reached your ideal results and replaced these power devices with these designs, can you help us understand what that increase in efficiency might look like?
Yeah, well, so that's probably not the answer you want to hear, in that it won't change that very much. The servers and the GPUs running that will still burn their 8 watts or 8 watt hours or whatever it was. But what the problem is that they're needing so much power now, and all of that power has to be converted, and along all of that conversion, there's losses. So with gallium nitride, you can make that, you can cut the losses in the transmission by about 30 to 50%. At the end of the day, it is still all getting burned in those servers. The other key part, though, is that as these servers are scaling, and really all of these electric applications, just delivering the power becomes hard enough as is. We need better switches to make that happen. And this was, one step in the right direction to make that happen. Thank you.
So you mentioned thermal behavior, and I was wondering if you could expand a little bit on the hotspot geometry between a HEMT and these devices.
Yeah, so in a HEMT, most of your heat is generated right by the gate there. It's kind of the highest resistant portion, and it makes a hotspot right near the surface that's covered in oxide, which is hard to pull away from the device. For these vertical GaN FinFETs, the hotspot is more generated in the bulk of the device, specifically with single crystal nice gallium nitride, where you're able to diffuse that a little easier. And then because it's vertical, it's conductive all the way down. So when these power devices are mounted, they're mounted on a package where you only have a heat sink attached to the drain, so the backside of the wafer, and you can't really pull much heat through the top side. So it brings that heat much closer to the actual devices there. That kind of starts to answer your question. Yeah, better thermal performance. And for people who aren't familiar with semiconductors, as these things get hot, it makes the resistance go up, and then they get hotter. So it just kind of runs away very quickly. So solving that problem is very important.
Final question.
So you talked about maybe being able to extend the superjunctions down to like 12 microns or so. Do you think that you would start running into issues with your fabrication techniques with like the shadow regions and stuff, or can that still support 12 microns?
No, so that's a good point there. So anytime that you have any very high aspect ratio features, it becomes hard to just get stuff down into the bottom of them. These trenches are, in this case, 8 microns deep, but only 400 nanometers wide. Just etching down into there becomes very challenging. The ions can kind of stray off to the side and hit the sidewall instead of the bottom where you want that to happen. And you notice that the etching rate decreases as you go deeper. So eventually you're going to have to make the opening a little bit wider if you want to go deeper. Or if you have a ultra low vacuum pressure in your RE system, you can kind of keep the ions more aligned with the fins and hopefully improve that. But it definitely becomes more challenging as you go deeper.
Thank you. And that's probably all the time we had for the open door. Oh, okay. There is question from Zoom. Okay. Last question from Zoom, please. Who
Is
can
somebody
read?
able to, I can't see that up here.
Rich Molnar.
Let me see what I got. Oh.
Hi, can you
We
hear
can
me?
hear you. Very good.
Yeah, I was
Go
just
ahead,
curious,
Rick.
have you thought about whether making the fins non-parallel, not non-straight, looking from the top, let's say sinusoidally, whether that would stiffen them up, and if so, how easy would that be to do, or how hard,
Yeah, I guess
or even cylindrical?
right. So the big problem with this is that we do need that TMAH wet etch to make the sidewalls very smooth, and that only happens along a particular crystal plane. So you want the M plane exposed along the sidewall there. So as you change the angle of that, it takes away your ability to make a smooth sidewall. And as these trenches get very deep, the etch gets very messy, and you really need to be able to clean it up with that wet etch. So what would actually probably have to happen is for structural support, just kind of cut out a portion of the diode and don't have fins there just to keep them all connected, and just do that every so often periodically to keep it kind of standing up straight.
So basically, nothing that 3 or more years in your PhD.
Exactly. Right.
Great suggestion, Rich. I think that's everything we have time for today. Let's please thank Josh again. And this concludes the open door session of the defense. So if the audience could please leave, we would appreciate that. Thank you.